A design review is not a ceremonial meeting where disciplines present slides, defend their drawings, record a few comments, and return to business as usual. A design review is an engineering assurance gate. It is where you deliberately expose the design to challenge before construction, commissioning, operations, maintenance, or an emergency exposes its weaknesses for you. If you manage engineering, your responsibility is not merely to schedule reviews. Your responsibility is to select the right reviews, conduct them at the right level of design maturity, bring the right people into the room, provide reliable inputs, force clear decisions, and ensure every action is closed back into the design. That distinction matters. A review conducted too early becomes speculation. A review conducted too late becomes rework. A review conducted without operations becomes theoretical. A review conducted without discipline leads becomes fragmented. A review conducted without action ownership becomes documentation theater. Every project does not require every review at the same depth. Smaller projects may combine reviews. Complex, hazardous, brownfield, offshore, process-intensive, or highly integrated projects may require several separate assurance sessions. The project engineering manager must determine applicability, timing, boundaries, interfaces, participants, and required outcomes through the project execution plan or project assurance plan. The first major review is the piping and instrumentation diagram review. The P&ID is where process intent becomes an integrated operating system. You review process, utility, demolition, and interface P&IDs systematically. You test compliance with project scope, the basis of design, design criteria, operating philosophies, customer requirements, system descriptions, and overpressure protection. You do not inspect only symbols and line numbers. You ask whether the system can start, operate, isolate, depressurize, drain, vent, control, trip, maintain, and recover safely. The process, mechanical, piping, instrumentation, civil, structural, operations, maintenance, startup, safety, and responsible system engineers must challenge the same drawing from different failure perspectives. The required outcome is simple: complete, accurate, coordinated, operable, and internally consistent P&IDs. The hazards analysis review then challenges the facility as an integrated hazard control system. For offshore and process facilities, the review must be systematic and multidisciplinary. It must examine process containment, ignition potential, shutdown, detection, protection, escalation, evacuation, and emergency response. It should follow completion or sufficient maturity of fire and gas cause and effect logic, hazardous area classification, shutdown analysis, escape and evacuation studies, and safety integrity assessments. The outcome is not a statement that the review was completed. The outcome is a report that identifies inadequacies, defines recommendations, assigns ownership, and records how the risk will be resolved. Next comes basis of design compliance. The basis of design is the contractual and technical memory of the project. If the BOD says one thing while calculations, specifications, data sheets, drawings, and vendor packages implement something else, the project is already drifting. You review the BOD section by section. You confirm that each discipline understands the requirement and has incorporated it into deliverables. You examine design changes and approved change notices, then update the BOD so it reflects the latest agreed basis. The test is not whether the document exists. The test is whether the design proves compliance. The layout review converts engineering intent into physical reality. You evaluate raw material flow, product flow, personnel movement, equipment spacing, hazardous separation, environmental effects, constructability, access, maintenance, local authority requirements, operational risk, future expansion, and interfaces between plant areas. A layout can satisfy equipment spacing rules and still be operationally poor. It can look clean in a model and still block crane access, maintenance withdrawal, firefighting, escape, cable routing, pipe stress flexibility, or operator visibility. The intended outcome is a facility layout that can actually be constructed, operated, maintained, expanded, and safely abandoned during an emergency. Discipline design reviews go deeper. For process engineering, you confirm that process flow diagrams are finalized, P&IDs are approved, hazard review actions are resolved, and flow rates, pressures, temperatures, densities, compositions, throughput, tankage, vessel elevations, utility demand, mass and energy balances, controls, emissions, vacuum conditions, and low temperature cases are properly defined. For piping, you confirm plot plan maturity, upstream data availability, design review action closure, code compliance, line conditions, seismic loads, wind, blast, snow, design life, testing, inspection, vibration, dynamic loads, standardization, constructability, and compatibility with existing facilities. For mechanical engineering, you challenge equipment location, material selection, inspection, statutory requirements, testing, vibration, operating parameters, design parameters, reliability, maintainability, operability, vacuum service, and low temperature service. For instrumentation and control, you review primary control variables, turn down accuracy, response time, dead time, loop interaction, valve metallurgy, seat materials, cavitation, flashing, sonic flow, pressure rating, hazardous fluid sealing, vibration, mounting, power supply, air supply, hazardous area suitability, maintainability, availability, and system interfaces. For electrical engineering, you verify demand, supply reliability, motor starting, fault levels, protection coordination, earth leakage, emergency power, future load growth, voltage regulation, lighting, earthing, step and touch potentials, lightning protection, insulation coordination, and hazardous area compliance. For structural engineering, you examine stability, strength, transportation loads, installation loads, operating loads, fatigue, corrosion protection, accessibility, dynamic effects, earthquake loading, temporary loads, permanent loads, constructability, offshore wave effects, vortex-induced vibration, marine growth, scour, and interference. For civil engineering, you challenge survey control, datums, setting out, traffic loading, equipment loading, hydrostatic loading, earthquake effects, geotechnical conditions, slope stability, drainage, erosion protection, strength, durability, subgrade performance, and material suitability. For marine works, you examine port layout, navigation, berthing, mooring, fendering, dredge depths, coastal effects, corrosion protection, utility services, weather windows, environmental impacts, flushing, constructability, maintenance, and operational management. The output from a discipline review must identify deficiencies and define the actions required to capture corrections in the design. A review without design incorporation is unfinished work. Material selection is different because it is continuous. Corrosion and material specialists should not appear only near procurement. They must be embedded in document checks for equipment specifications, material specifications, data sheets, requisitions, piping classes, vendor data, process conditions, and corrosion control philosophies. Material failure is often designed into a project long before metal is purchased. Incorrect metallurgy, corrosion allowance, lining, coating, welding, heat treatment, elastomer selection, chemical compatibility, or inspection strategy can create long-term integrity problems that are expensive or impossible to correct later. The next review is plant operability and maintainability. You ask whether the design is fit for purpose, energy efficient, comparable with proven solutions, expandable, commissionable, operable under normal, abnormal, and emergency conditions, and maintainable with realistic personnel, tools, access, lifting equipment, spares, procedures, manuals, and service support. Do not ask only whether equipment can be installed. Ask whether it can be inspected, removed, cleaned, calibrated, isolated, repaired, replaced, and safely returned to service. Operations and maintenance representatives are not optional guests. They are the people who will inherit every design shortcut. Dropped object and manual handling reviews challenge how equipment and materials will physically move through the facility. You review crane coverage, runway beams, monorails, trolleys, forklifts, lifting points, maintenance lifts, equipment change-out paths, temporary handling, swinging loads, dropped object exposure, crash protection, limit switches, weather restrictions, operator expectations, and interaction with fire and gas detection. You ask whether every foreseeable lift has been identified. You trace the complete lifting path. You challenge whether personnel are being expected to manually handle loads that should be engineered out. You verify that lifting activities do not create unacceptable restrictions or compromise protective systems. The process shutdown philosophy review defines how the plant fails safely. Starting from the highest shutdown level, you establish the hierarchy, boundaries, initiation logic, isolation requirements, interactions, escalation paths, reset philosophy, and relationships between existing and new facilities. You must examine normal operation, startup, shutdown, maintenance, partial operation, equipment failure, utility loss, fire, gas release, and emergency response. Any unresolved boundary must be recorded as a hold point with a named owner. Ambiguous shutdown logic is not flexibility. It is latent operational risk. The Telecommunications Review confirms that communications remain functional when they are most needed. You examine operational functionality, system architecture, coverage, performance, failure modes, power supply, backup supply, redundancy, vendor interfaces, emergency communication, and recovery. A communication system that works only during normal power and normal occupancy is not an emergency communication system. The Hazardous Area Review checks that area classification drawings are accurate, complete, and consistent with process sources, ventilation, equipment locations, P&IDs, layouts, and electrical and instrumentation selections. Misalignment between hazardous area drawings and the physical design can produce incorrect equipment certification, unsafe installations, procurement changes, construction rework, and compliance failures. Environmental control reviews challenge gaseous emissions, liquid discharges, solid waste, noise, energy use, regulatory commitments, customer objectives, and environmental hazards. You confirm that impacts have been reduced as low as reasonably practicable and that environmental requirements are embedded in equipment selection, process design, controls, operating philosophy, and monitoring. Environmental performance cannot be repaired by adding a paragraph to the operating manual after the plant is built. Fire and gas detection reviews examine whether the detection philosophy will identify credible gas, toxic, smoke, heat, and flame hazards early enough to initiate effective action. You review fire zones, detector type, detector distribution, voting logic, cross-zone interaction, redundancy, accessibility, testability, reset requirements, site interference, gas accumulation, dispersion, flare effects, vents, exhausts, solar interference, package interfaces, alarm actions, shutdown actions, and consequences when prescribed actions fail. Detector quantity is not the same as detection effectiveness. The question is whether the system can detect the right hazard at the right location within the required time and initiate the correct response. Active and passive fire protection reviews test hydrants, monitors, foam systems, deluge systems, water mist, inert gas systems, fire water networks, passive protection, water curtains, package systems, fire pumps, foam pumps, valves, routing, isolation, redundancy, vulnerability, hydraulic adequacy, surge effects, accessibility, initiation, and emergency power. You examine whether the system complies with the safety philosophy and whether deviations provide demonstrably equivalent protection. A fire protection system that is inaccessible, vulnerable to the same event it must control, hydraulically inadequate, or impossible to maintain is protection only on paper. Escape, evacuation, and rescue reviews begin with a brutal question. Can people escape from every occupied area during the credible event? You examine route width, height, directness, slip resistance, visibility, emergency lighting, signage, stairs, handrails, ladders, protrusions, trip hazards, fire exposure, smoke exposure, gas exposure, water curtains, heat shields, entrapment, stretcher access, breathing apparatus access, communications, control room escape, muster areas, sick bay access, and evacuation equipment. The review must be scenario-based. A route drawn in green is not automatically a survivable route. Finally, temporary refuge integrity and HVAC reviews challenge whether protected occupied spaces remain habitable during major accident events. You examine external walls, decks, doors, penetrations, ductwork, dampers, internal segregation, structural support, passive fire protection, smoke ingress, gas ingress, detection, isolation, shutdown, emergency operation, recovery, redundancy, maintenance access, equipment replacement, manual initiation, emergency power, and interaction with fire and gas systems. You review both normal HVAC operation and emergency modes. You test whether the system can isolate, maintain integrity, prevent contamination, support occupancy, and recover after shutdown. Across all these reviews, the operating discipline must remain the same. Define the scope, establish design maturity, issue the correct inputs, appoint a competent facilitator, record decisions accurately, include the disciplines that own the interfaces, bring customer, operations, maintenance, construction, commissioning, safety, and specialist representation where required. Then control the actions. Every action needs a clear statement, an accountable owner, a due date, a priority, a design deliverable affected, and objective evidence of closure. Closure does not mean somebody wrote completed in a register. Closure means the approved design has been changed, checked, coordinated, and reissued where required. You should also distinguish comments from decisions, recommendations from mandatory actions, and unresolved technical uncertainty from accepted risk. The real value of a design review is not measured by meeting duration, attendance, or the number of comments generated. It is measured by the defects removed, interfaces aligned, risks reduced, assumptions challenged, requirements verified, and lifecycle problems prevented. As an engineer, you must arrive prepared to challenge your own design. As a discipline lead, you must stop treating comments as criticism and start treating them as evidence that assurance is working. As a project engineering manager, you must prevent reviews from becoming isolated events. They must form a connected assurance sequence from design basis, process definition, layout, discipline development, safety systems, operability, constructability, maintainability, and emergency response, through to final action closure. The harsh reality is that most serious design failures are not caused by the total absence of engineering knowledge. They are caused by missing interfaces, unchecked assumptions, late decisions, weak ownership, fragmented reviews, poor action closure, and designs that were never challenged from the perspective of the people who must build, operate, maintain, and survive them. A strong design review makes those weaknesses visible while they are still affordable to correct. That is the objective, not to prove that the design is finished, but to prove that the design is ready to move forward. Turn File 0